I'm Frederick. I'm the founder of this company called Polar Signals. We work, unsurprisingly, on profiling. If you don't know what that is, don't worry about it. I'll go over that in a moment. Um, but yeah, so yesterday already we heard in a couple of talks about AI inference and performance optimizations of AI model inference. And obviously, in today's day and age, this is becoming more and more important. And so I want to lay out a kind of a scenario here where, we maybe have done all of the things that we heard in the talks yesterday, right? We've done quantization for the hardware that we're going to be running on. We're using all the latest versions of everything. We've done all of those things. So if we're at that point, maybe we're able to serve our model at, like, I'm making up some numbers, of course, but like maybe at 60 tokens per GPU per second. We're at 85% utilization of our GPU, so it's not terrible, right? Obviously, we would like to get that to as close to 100% as possible, because GPUs are freaking expensive. Memory bandwidth 70%. It's okay, I guess, but there's definitely room for improvement, and we've tried a couple of things, right? Like I said, maybe we've done quantization, but the kind of downside of that can be that we may lose quality for performance. We're kind of trading off potentially something. So not always ideal either. Maybe we've done a bunch of different things where we've tried to do batch size tuning, right? So all of these things are things that we should do and should try out. But once we're kind of at the point where we've tried all of these things, there's really nothing else other than actually profiling. And in the NVIDIA ecosystem, the tool that people typically end up defaulting to is called NSight. So this is a profiler that NVIDIA releases that you can use to profile your CUDA workloads. And the way that this works is, you launch your CUDA workload with this wrapper, and it starts profiling everything. So it looks at what are you running on your GPU, what is the memory bandwidth that's being used, all of these different kinds of interactions that happen with your GPU. It records it at a very high resolution, writes all of this data to disk, and then you can start to analyze this. The thing is, NSight kind of was born in a world where we don't necessarily have distributed AI training or distributed inference. And so much like, maybe people are familiar with perf within Linux, much like perf, it's kind of born in a world where, I'm running one application, I want to understand what this one application is doing. And that's a use case that NSight is great at. It collects very, very high fidelity information if I can run this workload kind of locally. There's some, maybe I'll make some people angry with saying this, but like there's some hacks that you can do to like run NSight in like your Kubernetes cluster and stuff like that as well. But it's really quite like patchworky solutions. And so my point is, doing all of this takes a long time, has a lot of rough edges, and maybe at the end of doing all of this, maybe we get an answer. So let's pretend for a second that we do, and we find out that in fact we were wasting a lot of time on a bunch of memory-related issues. Maybe we were also not using the right kernels because the software was accidentally falling back to slower kernels than we intended to. And so this doesn't look all that different from other like CPU-based workloads, right? Like memory allocations, memory copies are quite typical performance bottlenecks, whether it's GPUs or CPUs that we're working with. But like I said, this kind of workflow takes days to kind of go through. You need to set it up, you need to learn the tools, you need to gather all the data, you need to make sense of all the different things that happen on different machines. So we at Polar Signals basically said NSight, the way that it exists today, doesn't cut it. we kind of figured this was a tool that was born at a time when we didn't have distributed environments with GPUs. And so it's best suited for local development and not for these huge kind of cloud deployments. And at the same time, maybe sometimes we can reproduce things on our local machines, but nothing really quite behaves like production, right? So if there is an environment we truly want to observe, it is production. And so we kind of set out to ask ourselves, is there a possibility for us to create a profiler for the CUDA ecosystem that has very low overhead so that we can run it always on in production? And before I kind of dive into all the details, I think it's quickly important to talk about the kind of larger architecture of our open source projects and products. So the way that this works, up until this point, we've only created a CPU profiler for the same purposes, basically. And the way that you typically deploy this is you deploy our profiler on every single node in your system. Let's say on your Kubernetes cluster, you deploy it on every single node. It starts profiling everything that is on that host, and it sends all the profiling data to a central storage where it can all be aggregated and analyzed later. So just wanted to kind of demonstrate that this is kind of the deployment model. So like I said, we already have this profiler for CPU workloads. And we support a very wide range of languages, including, for the purpose of the CUDA ecosystem, probably, C, C++, and Python are probably the most important ones, right? We're starting to see a lot of Rust as well, actually. So that's a cool change that we're seeing. But realistically, probably 95% of all workloads use Python somewhere, and then and eventually call out to C++. So in case people aren't familiar with profiling data, this is what's called a flame graph. So the way that we read this visualization is, so it's kind of hard to see. Unfortunately, I can't zoom in because my computer isn't working. But the way we read this is kind of from the top down are the functions that end up calling each other. So up here, I know people can't probably read it, but it says main function. And from our main function, in our Python code, we call the train function. And the train function, actually does all the business logic that trains our model. And this is a CPU profile. And so it tells us where are we spending all of the CPU cycles during our training. And the width of these frames tells us how much time was spent by this function as well as all of its children. And so what we're seeing here is the data loader. This is a typical kind of training run as we would see it from the CPU perspective, because effectively all the CPU does, it loads some data, it puts it into some format, and then pushes it out to the GPU to process. And so that's exactly what we're seeing here. So that's great. But my point was, we can see these kind of Python functions here. And so this is work that we have already done. If you're really interested in all the work that went into this, we basically had to reverse engineer the Python interpreter and all this stuff to make this work. If you're interested in the nitty-gritty details about this, check out this talk that we did at FOSDEM a couple years ago. But yeah. So yeah. However, the problem was the Parca agent, the profiler that we work on, only supports CPU profiling. Well, hello. Until now. Just 2 days ago, we released this feature as part of the Parca open source project to actually profile CUDA workloads in an always-on fashion. So how did we manage to do that? So we basically looked at, well, what do other profiling tools do, right? Like fundamentally, there isn't a problem with the fundamentals that NSight uses. It's just the entire ecosystem around it. It wasn't built for this kind of scenario. So after a lot of digging, and there's not a lot of documentation around this, effectively what CUDA does, what NSight does, is when you launch your CUDA application, it launches it and automatically injects this environment variable called CUDA injection 64 path. And so whatever this path is set to, you essentially tell the CUDA library to dynamically load whatever this library is once CUDA is being initialized, and then we'll see what we can do with that. But that's ultimately the profiler interface, let's say. And so what happens? Like I said, when CUDA is being initialized, it calls dlopen on whatever this environment variable is set to. And then there's a single function that it calls called initialize injection. And this is ultimately the secret sauce. Because now what we can do is we can use this other function, ecosystem within NVIDIA called CUPTI, or the CUDA profiling tools interface, which we can use to instruct the GPU, because all interactions with the GPU are asynchronous. So we submit something, right? And eventually, at some point, it returns, but we have no idea when that happens. So CUPTI allows us to essentially say, okay, whenever you want to launch a kernel, make sure you notify me first with this and this information, providing me with that. So in our case, what we want is we want to know when are you going to launch a CUDA kernel or a graph launch. For those who are unfamiliar with this, I learned this as part of this as well. Basically, this kind of interaction with GPUs calling individual kernels is relatively expensive. And so what most workloads do is they pre-compute a graph of interactions that they want to run on the GPU. And then they submit this graph and say, just execute everything in this graph however you see fit. And then the GPU essentially ends up, or I guess formerly the CUDA ecosystem, ends up executing this entire graph. And this is far more common these days because all of these AI applications have been optimized quite a lot, and this has been kind of pretty early on figured out that this is a common bottleneck. So realistically, almost everything's a graph launch. So these are the two events that we listen to, and we asked CUDA to notify us whenever it wants to either launch a kernel or launch a graph execution, and then also tell us whenever any of these finish. So basically what that then looks like is we don't actually, so the reason why I wanted to visualize this is this isn't a shim where it's passed through. Even if we made some sort of programming error in our library that we've kind of loaded with this injection path, the worst kind of error that can happen is that nothing happens, right? It'll still end up calling everything in the with the GPU. So how do we then actually make use of this? So again, we haven't really talked about this because if I had to talk about all of these details, would probably need a 2-hour slot. But how do we make use of this data, and how do we actually then collect it? So we use a technology called eBPF. For folks who are maybe not familiar with this, it's kind of like a virtual machine within the kernel that we can use to safely extend the kernel. So in this case, this kind of from the eBPF documentation, we say I want to execute my eBPF program every time the syscall execv is called. So then that's kind of intercepted, and we can run our BPF program, and then it continues as usual. Why do I say this? Well, as part of our shim, because we somehow need to communicate this information from our shim to our actual profiler that a kernel was launched and that a kernel has finished, that we do using USDTs. These are kind of static trace points that we've instrumented our shim with, so that we can say, and we effectively call them every time a CUDA kernel is launched or a graph execution is launched. And then as we're listening to the completion of events, we also fire another trace trace point whenever that happens. And so what we do when we kind of put all of this together is we say, okay, notify us when a CUDA kernel is being launched. When that happens, kubectl does this kind of callback. That's when our trace probe fires. And at this point is when we do, and this is exactly why I talked about this earlier, we perform the stack collection. What was the function call stack that ended up leading to this point that called this CUDA kernel. So we save that together with something that thankfully the CUDA ecosystem has thought of, which is creatively what they call the correlation ID. This is the ID that you can then later, as executions finish, you can actually correlate these events with each other. So again, we kind of just save the stack trace together with the correlation ID, and then later when the kernel execution actually finishes, that's when we fire our second trace point in our shim, and we figure out, okay, this is the correlation ID that we previously recorded the stack trace for. So now, and it tells us also the start time and the end time of the kernel execution. So now we actually have a sample. We know what is the function call stack that ended up calling this kernel with this name. We know when it started, we know when it ended. So we've created a profiler. And just to kind of demonstrate that this also works for graph executions, it's a little bit more complicated, but in essence, not all that different. We just listen to, like I said, the execute graph launch call. At the top, basically everything exactly the same way happens, except that with graph executions, we never know when the full graph has actually been executed. So what we need to do is we essentially need to keep the stack trace around basically forever, and it's more like an LRU cache. We hope that by the time that it finishes, we still have the stack trace around, but we can never really know. However, in practice, it works out just fine. But what happens is for every single kernel execution as part of the graph call, we get a callback. So ultimately, it ends up being exactly the same, except we don't pay the price of launching each kernel individually. And so this is all pretty nice because actually all of the really hard stuff happens on the CPU and not on the GPU. And this is actually really crucial because it means we're actually putting only very, very minimal overhead on the actual GPU workloads. All the tracing happens on the CPU. And so this is how we're ultimately able to create a profiler that is very low overhead, but gets us all of this really crucial information to allow us to optimize our AI workloads. So what does this get us? Like I said, we get the start and the end times of kernel executions, whether it's a regular execution, whether it's a graph execution. We know what is the function call stack that ended up leading to this, but most importantly, this is kind of the goal that we set out to do. We can do this fleet-wide at very low overhead, and we can both get the visibility across what is the most expensive CUDA kernel executions that we perform across our entire system. We can see that fleet-wide, but also we can dig down into each individual node, each individual CUDA launch to understand and truly debug everything in detail as well. So yeah, that's what allows us to grab this kind of visibility whenever we truly need to. I have a tab open with some of this data actually. So unfortunately, what you're going to need to kind of imagine in your head is a pretty graph that also tells us the actual utilization of the GPU, right? And we can see when it's fully utilized or when it's not. And so therefore, we can look at what on earth is the GPU doing when it's not fully utilized, right? And so then we can get exactly the same kind of visualization. Actually, this is the CPU's time. Yeah, here we go. This is the GPU time. There we go. So yeah, basically here we can see exactly the same kind of first couple of frames, right? This makes sense. Ultimately, we end up calling train, but here we can see on the GPU, actually, the train part is actually not the part that wildly dominates. It's actually the test part. In reality, you know, there's a bunch of PyTorch stuff that we can't definitively assign. But the point is, at the bottom here, all the green frames that we can see, these are the actual CUDA kernel executions. So this is the type of insight that previously, you know, it was practically impossible to get at low overhead across your entire fleet. So again, we can now kind of go ahead and kind of slice and dice this through our entire infrastructure. We can look at an individual node. We can look at you know, data center A versus data center B. You know, maybe we have some new GPUs that we're trying out over here. Are they actually performing better, or you know, do we need to still do some more tuning? Is it actually using the right kernels for this particular hardware? All of these things we can now actually answer, you know, within minutes as opposed to days. So yeah, that's my demo. So with that, you know, now we all have the tools to optimize our AI workloads without compromise. Thank you.